In this short video we'll investigate the nature of the pi bond in an alkene, how it's formed and what that means for the molecule. Perhaps something that we knew from GCSE is that around each carbon in the carbon-carbon double bond the shape is trigonal planar, and that means that the bond angle around each of those carbons is 120 degrees. So here's a carbon-carbon double bond, and if we make it the simplest possible alkene, i.e. ethene, then what we're saying is that each of those 6 atoms that I've highlighted there, the 4 hydrogens and the 2 carbons, they are all in the same plane. So this molecule would lie flat on your desk. And each of those bond angles around the carbon-carbon double bond is 120 degrees. So how is the carbon-carbon double bond formed? Well, this diagram illustrates some p orbitals, and here we're saying that the p orbitals have overlapped to form a pi bond. Let's talk a little bit more about that. Let's consider the 2 carbons doubly bonded to each other in an alkene. I've just highlighted them in different colours so we can look at their electrons separately. So first of all, let's look at the purple carbon. So it will have 4 electrons. Now it's singly bonded to 3 atoms, so one of its electrons will make the single bond to whatever atom is on the end of that bond, one of its electrons there, and one of its electrons in the single covalent bond it has with the carbon. This means it will have one more electron in its outside shell, and that electron will live in a p orbital which is perpendicular to the planar molecule. So within that orbital, this electron will spend its time going north and south like so. Now the same applies to the green carbon. So it's 4 outer electrons. We have one which will be shared with that atom, one that's shared with that. There'll be one in the single covalent bond with the carbon, and then it has 1 electron left over, which again will go into the p orbital perpendicular to the plane of the molecule. And this electron will spend its time doing this. The pi bond forms, however, because rather than spending their time going up and down, the electrons find it easier just to move from side to side above the plane of the molecule. So these orbitals overlap to form the pi bond. So here's the pi bond in red, and you can see that it will contain 2 electrons. So we have 2 electrons in the pi bond, and then there's 2 electrons between the carbons in a single sigma bond. So 4 electrons altogether. So this is the high electron density that we'd expect in a carbon-carbon double bond. And if you imagine the pi bond a little bit like a hot dog bun around the sausage, which is the single bond. Now, one important feature of a carbon-carbon double bond is that this gives it restricted rotation. So if we take a molecule with a carbon-carbon double bond, and if we turn it into what looks a little bit like a person, so there's a slightly disconcerting face. So if you go out in the morning and you wear a pink glove on your right hand and a green boot on your left foot, a real fashion statement, then at the end of the day it would be very strange if they were on the same side of your body. So as you turn round, obviously they flip from side to side. Try it at home.